welcome to the calculator section. The fun part about the calculator section is you may need a calculator, you may not. And I have a feeling with this one, I won't need it. Given the function represented by the table above, what is the average rate of change between x equals 3 and x equals 7? Well, I have x and f of x. And the rate of change formula is f of b minus f of a over b minus a. You would be an a, you would be a b. So what I have to do is find out f of 7 minus f of 3 over 7 minus 3. F of 7 is 13. F of 3 is 7. 7 minus 3 is 4. 13 minus 7 is 6. And 6 over 4 simplifies to 3 over 2, which I didn't even have to do because 6 over 4 was an option. Interesting. I wonder why. But yeah, I mean, no calculator needed. You could have used one, but yeah, this one was fine without one. Hope this helps. The depth of water at the center of Lake Precalculus is modeled by a cubic function h of m, where h represents the height in feet and m represents the months of 2022. For example, m equals 1 corresponds to January and 2 is February and stuff. The data for the first 6 months of 2022 can be found in the table below. Use a cubic model to estimate the depth of Lake Precalculus in October 2022. So we care about October, which is 10. But what I need to do is it tells us right off the bat, it's cubic. That's what I was looking for. So what we need to do is we need to run to the calculator. We need to type this stuff in. We need to use cubic regression and use that formula to find what happens when I plug in 10 for m or x or whatever variable you use. Be right back. All right, let's talk about Lake Precalculus, which reminds me of my childhood. We go to stat, we go to edit, and let's plug in some numbers. The left side, pretty easy, just, 1 through 6 for January through June. Then you've got 41.6, 45, 45.8, 44.6, 42, Jackie Robinson, rest in peace, and 38.6. Now, this was a cubic model, so we're going to use cubic regression. And we're going to need to use that equation to plug in 10. So not only will I go to stat and calc and go down to cubic reg or just hit 6 or whatever your pretty little heart desires, we're also going to make sure that we go to store regression equation and save that equation because we're going to use that equation. So go to store reg eq, hit vars, go to yvars, hit function, hit enter, and now when you hit the y equals button, that gross looking formula, which is actually not that bad at all, will show up in y equals. Now, of course, if you're like, whoa, they're just being a tiny bit more specific than what that home screen showed us. Now, why am I going here? Well, my job is not to find the equation. My job is to find out what happens in October. So I can go to second, table, and scroll down to 10 and find out that October, which is 10, is 29, or 29.000000000000023, which I think rounds to 29. So I'll go back and see if I can find 29.0000000000023, or if it's just 29, then I guess I'll select that one. Well, they don't have 29.000000000000023, so I guess I'll select this one. But that's how you do it. Okay, cubic reg, do the store EQ. That helps. It's not necessary, but it helps. The function was friendly enough, but it made things just a teensy bit faster for me. Of course, I wasted all that time with all those zeros, but you know what? Hey, more zeros is more YouTube money. More zeros in my bank account. Hope this helps. The graph below shows a function f of x, looks like that, on intervals 0 is less than or equal to x is less than or equal to 13. So I care about stuff between 0 and 13. That picture checks out. 5 coordinates labeled BREAD. Sounds like a word. BREAD. Yeah, it checks out. One of the 5 points coordinates represents a local maximum, so that would be U. One represents a point of inflection, so that would be U. IP for inflection. You know what I mean. And 1 point represents a local minimum, that would be U. Let T sub B, T sub R, T sub E, T sub A, and T sub D represent the x coordinates at those coordinates. So you would be, I guess, I mean, it looks like 0, but instead of calling it 0, you would be the point like T sub A something, and you would be not T sub A, T sub B, because we're going in the words T sub R, and so on and so forth. It's kind of stupid the way they did that, but it looks like a problem on the practice test. That's why I did it this way. Of the following, on which of the intervals is the rate of change increasing at a decreasing rate? Well, if you're wondering, what the heck is increasing at a decreasing rate means? Well, a decreasing rate implies concave down. Increasing up implies going up and to the right. So increasing at a decreasing rate implies the left side of concave down. Now, the only spot that shows me the left side of concave down is in between B and in between R. You are decreasing at a decreasing rate. Now, this guy is concave up, so you are decreasing at an increasing rate, and you are increasing at an increasing rate. So this is what I want. I went between B and R. So they're not going to just be like, hey, select B and R. That's not how they want us to do it. They want us to say, all right, well, the x value for B is T sub B, and the x value for R is T sub R. So we're going to select A and only A. So where was the calculator necessary in this one? Nowhere. Nowhere at all. You will find that in the calculator portion of the AP exam, you're only going to use the calculator for about like maybe 60% of the problems, which you're like, oh, that's still more than half. It sure is, but it's not all of them. So don't go searching your calculator for something to do with this. There's no numbers except for these. It's just making sure you understand the vocabulary. Okay? Tricky, 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 weird, weird, weird. Hope this helps. Maria, you remind me of a West Side Story. Santana. Maria's bird watching and spots a bird in the air. Hi, Maria. Oh. The angle of elevation created by her line of sight and a line parallel to the ground is given as theta. So if you're like, this is the line of sight, her eyeball hitting the bird, okay, and as you can tell, and I'm not going to write it out, that's parallel to the ground, okay, you are going to be called theta. If tan theta equals 4/3, so tan theta equals 4/3, what is the slope of her line of sight? You ready to get out your calculator? Don't be. You don't need it. Tangent, by definition, means slope. When you get to calculus, one of the first things that you will learn is tangent means slope of a line at a point. Okay, so when it says the tangent is 4/3, that is the exact same thing as saying the slope is 4/3. So the slope of her line of sight is 4/3. And you're thinking, no way. There's no way this problem is as easy as saying tangent's 4/3, slope is 4/3. Yes, it's exactly that easy. Tangent means slope. Tangent means the change in the y values over the change in the x values. So this problem is done. No calculator necessary. That is it. Hope it helps. A data set is shown on a semi-log plot with a vertical axis scaled logarithmically. Okay, well, I don't see the semi-log plot. The points on this plot appear to demonstrate a consistent linear increase. Which of the following types would best represent the data set? Okay, well, I don't have a picture. I have a calculator, but I don't need it. If you have a semi-log plot, and I'm not even going to attempt to really draw this, but you might remember semi-log plots kind of start out here, and then things kind of like, simplify or get closer to that, and then this happens, blah, 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 blah. Well, if on a semi-log plot, you have dots going up and to the right, that does not indicate a linear equation because semi-log plots, their vertical axis are scaled logarithmically. So, and it says that right there. So this is not linear. What you have going on is exponential growth. Now, semi-log plots, when graphing linear-looking equations, give you either exponential growth or exponential decay. Why do I have growth? Well, this is going up and to the right. If these dots were going down and to the right, then you would have exponential decay. Okay? If these dots look like this, then we don't have exponential growth or exponential decay. And you're thinking, but it looks like exponential growth. I know, but if it's graphed on a semi-log plot, it's not because everything is scaled differently. So it's not quadratic. That's just a throw-in option that I gave you. But it's either going to be exponential or exponential. And in this case, it's exponential growth. So another one of those problems, that's a calculator section problem. Calculator wasn't necessary. We didn't even have a picture, but we didn't need one because my art did the job just fine. Hope this helps. A particular bank offers a newborn account promotion that gives the family of a newborn a $100 account with a biannual compounded interest rate. The formula the bank uses is A of y equals 100 times 1 plus r over 2 to the 2y. So this is a typical compounded interest rate formula. If you have heard of the continuously compounded interest formula, there's similarities, okay? But this is not the continuously compounded interest formula. This basically says, like, I put $100 into the bank and I check a half a year later and I have a little bit more. And then I check 6 months after that and I have a little bit more. But we really don't need to worry about that. What we need to worry about is A of y is the total amount of money that you have in the account, not how much you make, your value of the account. R represents the interest rate as a decimal. So if your interest rate is 2.5%, you move the decimal to the left twice and R will equal 0.025. Okay, we'll get there when we have to get there. Y represents the years the account has been used. Okay, so everything so far gross but makes sense. If an account opened for 13 years has the amount of $108.52, what would the average rate of change be from the 14th year to the 18th year? This is going to be a nightmare, but I'm here to guide you. First things first, I don't know what R is, but in this part, I can take y is 13. Usually I use t for these problems, but y is 13. And this would be a of y and set up an equation. So 108.52 is going to equal 100 times 1 plus r over 2 to the 2 times y, which is 2 times 13. I could do two things right here, so I'll do both of them. I could divide both sides by 100. So now I could do this in my head. That's just going to be 8.52. I mean, you could use a calculator, but the numbers are friendly enough where I could just do that. No, it won't. It'll be 1.0852. Ugh, silly me. I can divide this in my head. I mean, dividing by 100 just has you move that over twice. So that becomes 1.0852. You could use your calculator, but I don't want to have to go back and forth when I make these videos. 1 plus r over 2 to the 26th. All right, now let me take this guy and rewrite it over here with all of this space. We are going to do something that you've probably never done in class. Maybe you have. Maybe you haven't, but my issue right now is I have an R trapped inside a parentheses. I need to bring this 26 down. Somehow I need to bring it down. So this is what I'm going to do. I'm going to ln both sides. By ln'ing both sides, I can bring that 26 out in front. So now I have ln of 1.0852, whatever that is, equals 26 ln of 1 plus r over 2. There you go. Now what I can do is I can divide both sides by 26. Cross u out. That leaves me with, and this is awful, ln of 1.082 divided by 26, 0852 divided by 26 equals ln of 1 plus r over 2. Let's run to our calculator and find out what ln of 1.052 is divided by 26 real quick. All right, ln of 1.0852, close it, divided by 26. Enter is going to be 0.0031, blah, 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 blah. So I'm going to actually write out as many of those points down when I go back and do the problem. All right, let's move everything up here, cut u off. Right there, we have ourselves. And actually, let me erase this to give myself more space, because even when we finish this and find out what r is, we are certainly not done yet. It's a gross, gross, gross problem. We ended up with 0.00314478. I'm going to write out all of that. Does it seem like a lot? Do I care? No. That's going to equal ln of 1 plus r over 2. Now I need to unlock that r. So what I'm going to do is I'm going to e both sides. So you're going to be e to that gross number equals that. That allows you two to cancel each other out. So I have e to the 0.00314478 equals 1 plus r over 2. Subtract 1 from both sides. Equals r over 2, and multiply both sides by 2, and you can now find your r. Okay, so that looks awful, but I'm going to run to my calculator and find out what 2 parentheses e to the 0.0 minus 1 is, and that gives me r as a decimal. Be right back. All right, here we go again. 2 parentheses. The e to the is that button right there. And it's going to be 0.00314478. Okay, let's hit right. Let's subtract 1, close it, hit enter, and we get 0.006299. So let's do that. 0.0. Let's do the whole thing. Freak it. Freak it. Let's do the whole thing. I apologize for my vulgar language. The rate as a percent is, or not as a percent, as a decimal is 0.006. Actually, the numbers, I know I said freak it a bunch of times, but let's keep it like that. 63. So that's basically 0.63%, not a strong rate. Now, this is what I have to do. Now that I know that r is this, I'm not even done. I have to run to my calculator and let me get rid of this mess up here, blah, 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 and let me use this equation in my calculator. 100 times 1 plus 0.0063 over 2 to the 2y. We're going to use that to find the average rate of change from the 14th year to the 18th year. So I don't have to go back and forth a ton of times. I'm going to do that formula, find out a of 18 minus a of 14 over 18 minus 14, which is 4. So this is going to give me some terrible number. Okay, divide that by 4. And that'll see my average rate of change. It's not going to be a lot, but let's see what happens. Oh my gosh. So let's graph that terrible, terrible, terrible equation. 100 parentheses 1 plus parentheses 0.0063 3 divided by 2, close it, okay, to the 2, I know it says y in the problem, but it's to the 2x. Okay, so just making sure everything looks good. The graph won't help us. What I need to do is find out what A of 18 is and A of 14 is. So let's go to my table. A of 18 is 111.99. What a convenient number. 111.99. And A of 14 is going to be 109.21. So let's go back, parentheses, 111.99, 111.99 minus what it was 14, 109.21. And we're dividing that by 4 because of 18 minus 14. 0.695. Now, this is money, so 0.695 means 70 cents. So after all of that, well, let's go back and I'll explain what the problem is. We'll select 0.70 and we'll explain what the answer means in this context of the problem. All right, so B is our guy. So after all of that, what this means is this bank account that you're given for free is only going to get you about 70 cents a year once you hit your teenage years. That's not a lot. And banks kind of work that way. They kind of rip you off. Okay, so, store your money in treasures in heaven. I think the Bible says that, but, whatever. So that's this problem. This problem is like, here's an account. If you're a 13-year-old and you only make $8 after, you started out with 100, what are you going to expect to make, like $100 a year? No, in this case, it's 70 cents. So terrible, crazy, terrible problem. But we got through it. So hope this helps. A particle is moving along a curve and its position is given by s of t units. The velocity, also known as the rate of change of the particle, is given by the equation v of t equals 0. Blah, 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 blah. For 0 is, or t is between 0 and 14, but not including. I probably could have included those. Doesn't make a difference. Which of the following is true about the position of the particle? This is a problem that I made and I was inspired by calculus. They love to give you the particle velocity type questions. And this is what the question is asking. It's giving you the velocity function, right? Now, the velocity of a particle is also its rate of change, also its slope. So we have to understand that if the velocity, okay, also known as the rate of change, also known as the slope, if the slope is negative, okay, if the slope is negative, that means its position has a negative slope and its position is going down. Now, what that means with a particle is a particle can like go up, down, we don't know. But if the velocity or the slope is negative, the position means it follows a negative slope. It's going down. If the velocity, also known as the slope, is positive, okay, that means its position is following a positive slope, so it's going up. So there's two things that we're looking at here. Okay, one thing is this picture that I kind of drew here. So thing number one is if you have a negative velocity, a negative v, and then all of a sudden it changes to a positive velocity, positive v, you have yourselves a minimum. Okay, you have yourself like, okay, well, here it is. If the particle's moving along at a position, that's what happens when your velocity or slope changes from negative to positive. Similarly, if our velocity goes from positive and then all of a sudden changes to negative, we have ourselves a maximum, local maximum. So maybe something like this. Okay, so what we have to do is we need to graph this. We need to graph the velocity function and find out where it's positive and find out where it's negative and find out where that change is. Okay, because if it's positive and then becomes negative, then it looks something like this. Positive slope, negative slope, we have a maximum. If it's a negative slope that changes to a positive slope, we have a minimum, and we could probably answer these questions here because these answers are talking about zeros and local minimums and maximums and stuff like that. So let's run to our calculator and see what happens when we graph that guy right there. All right, so we are looking at graphing that velocity function, which was pretty unpleasant, but we'll be all right. 0.765, it says t, but t is x, minus 2.654. 2.654. Now, before I even graph this, we care about magic happening between 0 and 14. So let's change our window from 0 to 14, like so. Let's hit graph. Now, remember what I said on this slide. When you have a negative slope, that means your actual function is going down. When we have a positive slope, that means our actual function is going up. So here is a negative slope, here is a positive slope, and we should probably find out where that changes. So second calc 0 will tell us where our slope, or this velocity function, which is the slope, changes from negative to positive. So if we put the left bound to the left of it, put the right bound to the right of it, and hit enter for guess, we have 3.469 or 3.469 is where our slope goes from negative to positive. So let's go back and try to diagnose what that means. All right, so as you can see from the multiple choice options, 3.469, the number that we saw in the calculator, is going to help us out. What we saw in the velocity graph that we drew in the graphing calculator, or saw in the graphing calculator, is the slope went from negative to positive at that 3.469. Okay, so that 3.469 is telling us that we have something that looks like this, so I can get rid of you because you're no longer a viable option. We have a position where this particle is like traveling down some type of roller coaster and hits the very bottom at time 3.469 and then goes back up again. So this is a local minimum at 3.469. So the particle's position is 0 at 3.469. No, that's not true. The particle's position is at a local maximum at 3.469. Nope. The particle's position is at a local minimum at 3.469 because the velocity, also known as the rate of change, changes from negative to positive at that value. That's my guy. The particle is always increasing because the velocity is always increasing. No. The velocity always increasing has nothing to do with where your position is. It just means you're speeding up. And if you're going down a hill, you're probably going to speed up at some point. So yeah, there you have it. Very strange problem, very different problem. But this problem mirrors a similar problem on the second or AP classroom practice test, whatever it's called. So yeah, I'm not just pulling this out of thin air. It's something that you could possibly see. So hope this helps. Certain points of a rational function g of x are displayed in the table below. Which of the statements is true about g of x? Well, let's see what we have. We have x values that go up by very small increments. And as the x values go, and it looks like this is pretty consistent, they go up by 0.1 every single time. Okay. This goes up by 0.2 every single time. Except for right there where it's undefined. Now, what that tells me is you have some type of graph that it goes up 2 over 1. So you have some type of graph that goes up 2 over 1, and then all of a sudden it blanks out at 4. Now, if something is undefined, you're looking at two options. Option number 1 is a vertical asymptote, and option number 2 is a hole. Now with vertical asymptotes, this is what you're going to see. You have two options for vertical asymptotes. As things get closer to that magic number, these y values, in our case, g of x values, are going to explode and then all of a sudden just reappear down there at the bottom. Or if your multiplicity is 2, your numbers are going to explode and then level out. That's not what we have here. We don't have a picture like that. What we have is a picture where if it's a whole, things seem pretty consistent until all of a sudden it's undefined and then it keeps going. And that's what we have. This stays very consistent. It's very linear until all of a sudden it's undefined, which tells me at 4 you have a whole. Okay, so not a vertical asymptote, not a horizontal asymptote. Yes, a whole and not a 0. If it was a 0, this would say 0. But again, what vertical asymptotes are going to do is this number is going to be regular and then a little bit bigger and then a little bit bigger, then huge. And usually when they give you graphs where it gets huge, they'll say stuff like, 3.9 is like 100, and then 3.99 is like 1,000, and then 3.999 is like 10,000, and then all of a sudden 4 is undefined. So that's usually the vertical asymptote type problem. We didn't have that at all. This is a whole type problem. Where did I need my calculator? I didn't. Once again, this is one of those problems where you don't need a calculator even though it's in the calculator section. Okay? Hope this helps. The table below represents values of a logarithmic function. Look how small it is. Why did I make it so small? Use logarithmic regression to predict the y value when the x value is 654. Geez Louise. All right, so what I'm going to do is I'm going to use that table right there and use what's called ln reg. What that's going to give me is that's going to give me some gross-looking ln problem. I'm not going to write it down. I'm not going to save it. I'm just going to store it and then plug in 654 and see what happens. Be right back. All right, ln reg is just like any regular regression, okay? You go to stat, you go to edit, you type in your numbers. Now, you know this is logarithmic because you'll see as I type in the x values are multiplied by 4, okay? And the y values just go up by 2 every time. That's what makes something logarithmic. If the y values increase by the same constant number for every equal value interval and the x values explode, that's logarithmic. The reverse of that would be exponential. Now I'm going to go to stat, and ln reg is 9, so you can either hit 9 and scroll down to it, whatever you want to do. For store regression equation, I'm going to go down and I'm going to go to vars and store this. So vars, y vars, enter, enter. And now when I hit calculate on this guy, I don't have to write this whole mess down. Now, usually when I do problems like this, and let me go to y and just show you what I mean. Usually when I do problems like this, I go to my table and I scroll down to see what I need. Well, in this case, I'm looking for 654. So if you're thinking, oh, I'll just find the values, second calc value, that's a great idea. Here's the problem. If you type out 654, it's going to yell at you. It's only going to give you the values that the table covers. So I need to change the window to make sure that I have 652. So I'll change it to 700, not 100, 700. Hit second calc value again. Type that number 654, hit enter, and I get 17.35, blah, 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 blah. So that's what I'm going to get. I'm going to go back, select that answer, and I'll be done with it. 17.345. Yeah, I wonder if maybe I put in one of these wrong, or if maybe when I created this problem it was slightly off, or maybe, I don't know. I don't know what I did wrong, but clearly this is the answer that I want. Maybe I just mistyped it. But yeah, there you go. ln reg. Fun stuff. Hope this helps. The polar function f of theta equals r equals 2 minus 3 sine theta is graphed in the polar coordinate system on the interval between 0 and 2 pi. On which of the following intervals of theta is the distance between the point with polar coordinates and the origin increasing? All right, so this is what it's asking. This is a very confusing problem, but let's try to understand what the question is asking us. If you were given a polar graph, right, and you start graphing the polar graph, and you start way out here, and as you move counterclockwise, it moves its way in, your distance is decreasing. Now, what that looks like, okay, so again, as you move counterclockwise, this curls in, you're decreasing. What this looks like on the rectangular system is you start up here and you work your way down, okay? As you move towards the x-axis, you're decreasing. What that also means is if you were to draw this out and keep drawing this out, this too is you working towards the x-axis. So you could be in negative land, you could be going this way in negative land working towards this, and that's you also decreasing. So if your graph in the rectangular system is moving towards the x-axis, your point is decreasing. That's not what we want here. We want increasing. So what that could look like is maybe you have a polar graph and maybe you start at 0, 0, and as you move clockwise, it kind of gets larger like that. What that looks like is, again, you start at 0, 0, and you're moving away from the x-axis, okay? So that is an example of increasing. So we need to find out where we're moving away from the x-axis. Okay, so it could look like that, or it could look like that. Okay, so we're going to run to our calculator. We're going to graph this guy out. Okay, and we are going to find out where our curve is moving away from the x-axis. Here we go. All right, you ready? We are going to graph 2 minus 3 was it cos? Sine. Ooh, that was a close one. Sine and an x, because we're graphing this on the rectangular system. So I'm going to change my window. Actually, I'm going to go to zoom and do zoom trig and then change my window. All right, so as we can see, it bottoms out at -1. It looks like it goes up beyond whatever this number is. So I'm going to go and say, let's move this from -2 to, I don't know, 6 should probably do the job. Also, I care about stuff happening between 0 and 2 pi. So let's change that to 0 and 2 pi and hit graph again. Now, what I said is we care about where things are moving away from the x-axis. Interval number 1 is going to start from here and end here, because at this small, tiny curve, we are moving away from the x-axis. So I need to see what that is. So that is a 0. I'm going to hit second calc and go to 0, which is the second one. I don't know why it took me forever to look for that. So let's scroll over. Let's scroll over, hit enter, and it begins moving away from, it begins increasing, I guess I should say, at 0.72, blah, 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 blah. And it's going to stop increasing right here at the minimum. So let's do minimum. Boom. Let's move to the left. Hit enter. Move to the right. Hit enter. And we get 1.57, which is half a pi. So it looks like magic happens from 1/4 of a pi, that 0.7 to 1.57. So that's our one thing, 0.7 to 1.5. Okay, I'm not going to have that memorized. You'll see it when we get back there. Now it starts increasing again from here to here. So I need to find that 0. So I'm going to repeat the process. Second calc 2. Okay, find that 0 right there. Enter, enter. So 2.4 whatever, okay, is where I start increasing again, and it stops increasing at that maximum. So second calc maximum. Let's move to the left. Enter. Move to the right. Enter, enter. 4.7. So we add like 0.7 to 1.5, 2 point, I don't remember, to 4.7. Let's go back and answer that. All right, so I hope your memory is pretty good, but that's the guy we got. Okay, so again, the picture that this looked like is from 0.7 whatever to 1.5 whatever. It looked like that, and then it came back up and went way up here at 2.4 to 4.712. So C is going to be our guy. Very tricky, very challenging problem, but again, all the problems that I make are taken kind of from the test with changes. Okay, so I hope this helps. A pot of water is placed over a fire until it begins to boil. The function T of m equals 2.169 sine inverse of 0.132 m plus 0.77 gives us the temperature of the water T in degrees Fahrenheit and hundreds from the time 0 to 5 minutes. Awesome. Gross. Approximately how many minutes will it take the water to reach 100 degrees Fahrenheit? So this isn't so bad. We're going to graph this in our graphing calculator in y sub 1. Now, since the temperature is given in hundreds, in y sub 2, we are going to graph 1.5 because 1.5 hundreds is 150. I'm going to find out where these two guys intersect, and that's going to give me my minutes. So let's go and do that. Okay, you ready to... All right, y equals 2.169. Inverse sign is second sine. There's my inverse sign. 0.132x. So I'm going to make sure I hit that. Close it. Plus 0.77. The other graph that I said I was going to make is going to be 1.5. Okay, so let's hit graph and see what happens. Okay, so we get right there almost right away our intersection. We need to find out where they intersect. So second calc 5 takes us to intersect. Let's move just to the left, enter, and just to the right, enter. Hit enter again, and we get 2.50183, blah, 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 blah. So x is going to be that 2.5 answer. Let's go back and circle it. All right, 2.501 stuff is going to be 2.502 once I round it. So pretty weird problem, but not too bad. Just use your calculator. Hope this helps. The last problem of the calculator section, and the MCQ, as the kids say. The graph below shows the rate of change of profits for a particular store in thousands of dollars for the first 8 hours that the store is open. Which of the statements can be true based on the graph? So let's look at the graph. Now, this graph is not profit. This graph is rate of change. Okay, and what it looks like here is we're dealing with if I'm thinking rate of change and I'm looking at words like increasing and decreasing and stuff like that, I'm thinking concavity. So let's remind ourselves what concavity looks like. This is concave up. Concave up is when the rate of change is increasing. This is concave down. Concave down is when the rate of change is decreasing. So when I look at this picture, okay, my rate of change starts out concave up, and then it looks like, let me get a thicker line. I meant to get a thicker line. I just missed it. It looks like it's concave up until like right at 2, where we hit an inflection point. Rate of change is increasing when it's concave up. Rate of change is increasing when it's concave up. Then all of a sudden it's concave down until 4. So this is decreasing. Now it repeats the process. The rate of change is concave up, so this appears to be increasing right here. The rate of change is increasing, and then the rate of change is decreasing from 6 until the end. So the rate of change increases from 0 to 2 and 4 to 6. The rate of change of profits is increasing from 0 to 2 and 4 to 6, and the rate of change is decreasing on intervals 2 to 4 and 6 to 8. C is my guy. No calculator needed. Pretty gross problem, but boy was it fun. It really wasn't. I hated it. But, as always, I hope this helps.